Hi, this is the video for introducing our project about genetic adversarial attack with Pareto optimization. We are Team 12 and I'm Park Seung-gun, who is in charge of giving you the project pitch this time. Before we get to the actual problem solving, I'm going to skim over some basic concepts. First of all, what is adversarial attack? It's an attack on deep neural network model or DNN model for short. To generate adversarial attack, the attacker has a slight change in the input data. If you look at the picture, you can see that by adding a fine noise, DNN classifies the image into a picture of gibbon, while it still seems to be a picture of panda in human eyes. This kind of misclassification problem can be quite severe, especially when it comes to field of security, automation, and so on. There are two types of adversarial attacks, white box attack and black box attack. If the attacker has information about the target model, it's called white box attack. The required information can be an algorithm used in model training, training data distribution, or hyperparameters of fully trained model architecture. On the other hand, if the attacker has no such information, it's called black box attack. Because there is no clue to the internal structure, the only way to attack is to observe the outputs obtained by injecting the manipulated inputs and figure out the optimal manipulation to cause misclassification for DNN. Then how can we assess the effectiveness of an adversarial attack? This has to be done by two metrics. One is attack rate. It's a percentage of successful attacks in misclassification inducement. Of course, the higher it is, the better. The other one is perturbation, which is the difference between the original input and the manipulated input. Different perturbation evaluation metrics are used according to the characteristics of the algorithm. As you can guess from the previous example, good manipulation should not look much different from the original. Therefore, the lower it is, the better. Remember that to get one of them, you have to give up the other to some extent. I guess you are now ready to take a look at our problem more deeply. Now I will introduce you to a black box attack algorithm called POBA-GA. This algorithm uses genetic algorithm to generate optimal adversarial examples. In more detail, generation consists of different noise features. These noises are added to the input to get the fitness values. And then typical operations of GA like selection, crossover, mutation are followed. On the right side of this slide, you can see its unique fitness function. And you can also find out that attack rate and perturbation are optimized simultaneously by giving the perturbation value, also called G-score, a negative sign. Here the G-score is designed to better model the naked eye detection of perturbation, while other popular algorithms just use L0, L2, or L infinity norms as metrics. We are going to talk about this later. So what is the problem of POBA-GA and how can we solve it? Basically, there are two goals in adversarial attack. First one is attack success rate and second one is perturbation size. The ultimate goal of the attack is maximizing attack success rate and minimizing perturbation size. However, traditional optimization methods use only weighted sum for fitness. As we learned in class, we cannot say that one of these solutions is better than the other. Therefore, we can apply NSGA2 to adversarial attack with GA to get Pareto front. To abstract our problem definition, we try to mix three elements: adversarial attack, genetic algorithm, and multi-objective optimization. First, there are so many researches between MOO and GA. NSGA2 is also one of the fusion of two fields, and this kind of fusion is very popular. However, adversarial attack became famous within recent few years, therefore fusion between adversarial attack and GA or MOO is not popular, and there are only some fundamental tries in this fusion. In this point, our problem definition is fusion of these three fields, and this is not yet researched well. There are only some fundamental researches and there are no comparison between GA and MOEA. By merging and comparing these three fields, we expect to get better viewpoint to analyze adversarial attack with genetic algorithm. Next, I will explain how we are going to evaluate our methods appropriately. The first evaluation target is evaluation dataset. Each of three vision datasets have different number and kind of classes with a distinct resolution. Each of them is called MNIST CFAR10 ImageNet 64. MNIST dataset contains 10 class digit image with each image resolution of 24 by 24. CFAR10 dataset contains 10 class object image with each image resolution of 32 by 32. ImageNet 64 dataset contains 1000 class object image with each image resolution of 64 by 64. The recognition difficulty is determined by various factors: image resolution, the number of classes to classify, the size of dataset, and so on. For example, the image has less information as resolution is getting lower, and the dataset size is getting smaller, and finally, it leads harshness of recognition. By testing the algorithms on the three distinct datasets, we will be able to test the robustness of the datasets. The second evaluation target is evaluation models. In the deep learning field, each of the models is constructed by the different structure. So each one of them focuses on the different features of the image since they have their own mapping functions of images. For example, a model A can recognize the car by focusing on the wheel, while model B can recognize the car by focusing on the car frame. We will test the adversarial attack algorithms onto various models: VGG19, ResNet 50, Inception v3. Therefore, we can test the algorithm robustness on the model. The third evaluation target is evaluation algorithm. As we mentioned in the introduction, adversarial attack can be divided into white box attack and black box attack. We will check the advantage of our algorithm by comparing currently existing black box and white box algorithms. Especially, we can show our algorithm's superiority by directly comparing it with POVA-GA. Also, it may be meaningful to show how much our black box algorithm reached the white box algorithms on the performance perspective. We are going to evaluate three major degrees for each model. Most of ML models with adversarial attacks use L0, L2, and L infinity norms to calculate perturbation size. L0 measures number of pixels changed, L2 measures Euclidean distance between two images, and L infinity measures pixel perturbation. But most of the algorithms use different perturbation sensitivity. Plus, previous L0, L2, or an L infinity approach could not compare amount of perturbation precisely. Therefore, POVA-GA proposed G-score, which compensate problems made by those L series and superior in both naked eye and machine perspective. G-score has more in line with human eye to perturbation, and it can also distinguish small perturbation, making samples perturbation smaller. Attack success rate was measured to evaluate attack probability for each model. Since we focused on black box adversarial attacks, to get sample from model we make queries to mode. Usual adversarial attack requires excessive number of queries for high attack success rate. We are going to measure query count to compare the models. In conclusion, we will compare the final result by evaluating different metrics on the various datasets, models, and algorithms. This is the end of the video. Thank you for watching.